Allison Dorley, and I will be moderating today's webinar. Before I hand over to our presenter today, I'd like to go over a few housekeeping items. First, at the bottom of your screen, you will find multiple application widgets you can use. All of the widgets on your screen are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking the arrows in the top right corner of your slide widget. If you have any questions during today's webinar, you can submit them through the Q&A widget and we will address them at the end of the presentation. If we do not get around to your question, please know that we will capture all of them and we will answer via email if we run out of time. A copy of today's slide deck and additional content regarding our topic are available in the resource list. We encourage you to download or visit any resources that you may find useful. An on-demand version of this presentation will be available following the webinar and can be accessed using the same link that was sent to you before the event. For best viewing experience, we recommend using a wired internet or strong Wi-Fi connection and closing any programs or browser sessions running in the background. These may use a lot of bandwidth. Some networks cause slides to advance more slowly than others, so logging off VPN is also recommended. If your slides are a bit behind, pushing F5 on your keyboard will refresh the page. The webinar is being streamed through your computer, so there's no dial-in number. For the best audio quality, please make sure your computer speakers or headset are turned on and the volume is up so you can hear the presenters. You can find additional answers to some common technical issues located in the help widget that looks like an exclamation point located at the bottom of your screen. If you are interested in downloading the certificate of attendance for today's webinar, it will be located at the end of the event in the certificate widget. Just make sure to click on the certificate icon, and will also be emailed to you if you participate in at least 45 minutes of today's event. And lastly, we would appreciate it if you would take the short survey when you close out of the webinar. Now that we've covered all of that, let's get to the reason everyone's here today. Today's webinar presenter is Thomas Schultz. Thank you for joining us today, Thomas. Take it away.
Thank you, Alison. As mentioned by Alison, my name is Thomas Schultz. I'm the Manager for Marketing and Sales for the GIS product portfolio for Hitachi ABB, North America, and operating in the GIS business since, in the meantime, more than 18 years. Let's start our presentation with a safety moment. And as we are talking about gas insulated substation, I thought it would be a good time to talk about safety in regards to gas insulated substation. In respect to this case here, it is an issue happening at a substation in Singapore. At the 220 kV substation GIS installation, what happened that the personnel was operating or maintaining the equipment, exchanging moisture absorbers on the equipment. While the people were removing absorbers at the equipment which was depressurized, one person was actually taking it a step forward and tried to remove an absorber from a non-depressurized compartment, releasing 13 kilograms of SF6, which relates to 286,000 kilograms of CO2 in equivalent, and of course potentially harming the personnel himself and the personnel around him. The takeaway from this incident is for absolutely sure communicate each and every step with all personnel on site. Make sure only trained and certified personnel is operating the equipment like it should be for each and every substation, whether conventional or GIS, and make sure that you have clear working processes in place. That means that people are aware they have to read the pressure in the gas compartment before loosening any screws and bolts. In this case, the substation was de-energized, so there was no former harm in that regard, but it had definitely potential for a major incident. Talking about GIS and talking about the needs for the technology on the market. we all see globally the same picture with aging infrastructures at utilities, power suppliers, at industrial applications. Equipment is aging, has to be maintained, and that is definitely something which is affecting globally utilities and power generation. Another aspect is increased need for availability and reliability of a power supply. While it might have been years ago not that drastic to lose an outage in today's world with data centers connected, people become more in need of the electricity, of the power supply. And power outage is taking much more serious than it was maybe 30 or 40 years ago. It is a requirement to see the power without any outage in the supply. Looking at the outages, we also request that we have a speed of responsiveness, that we have local certified personnel available which can operate the equipment, which can maintain the equipment. We see environmental aspects. Now we see more and more awareness of the global warming. We see discussions pretty much every day in television and radio. We follow this discussion. And last but not least, we have an issue with real estate substations, which we are a couple of years ago in the middle of a farm, are surrounded by housing, and nobody is keen to have a new substation in his backyard. Now, we might have actually a solution here with a technology which helps at least to address some of its items. And I don't want to say it is a perfect solution for everything, but it might help to find certain applications. And let's start with the idea of what actually is the difference between a conventional substation, air-insulated substation, which is well known on the market, and a gas-insulated substation. Air-insulated substation, as the name says, is air-insulated, which, by the way, is also gas, but the gas is at the open air. That means it's atmospheric pressure. That means we see on the left picture, we see that the conductors are high up in the air, supported by insulators to ensure the necessary clearance, safety clearance, and clearance between the conductor is in place. For a 345 kV, for example, the safety clearance is 15 feet. So just as an example, if you go to the right side, it's the same voltage level, but in a gas-insulated substation. And what is done here? Insulating gas is compressed around the conductor. So the conductor is held in place by insulators inside of aluminum tubes with compressed either SF6 or our gas in today's world. The safety clearance, for example, on such an equipment, we are talking about inches, even if it's the same voltage level. And with that reduction of the size, with that reduction of that safety clearance, we are actually creating the advantages of this technology of a GIS. We started already with a safety moment, but I didn't want to take one of the advantages away. With a GIS, actually, we are creating a safe environment within our substation. That GIS is designed that every operational personnel, maintenance personnel can safely walk around the substation. We see the person on the left, for example, touching the equipment. That equipment is fully touch-proof. It's like a shielded wire. You have a grounded enclosure, you have a live conductors inside. All the enclosures are arc-proof. So even if a failure happens inside, you will not have an explosion of an enclosure. It's an arc-proof enclosure. All the interlocking features which you have in typical substations are taking over into the gas-insulated substation. So you have an interlocking between the disconnect switches, interlocking between the grounding switches, breaker, fast-acting ground. Everything is interlocked, can be padlocked for the maintenance operations, can be tagged out, locked out, as you have your typical procedures. And you have few ports to verify the switch positions of this disconnect and grounding switches. Another aspect is the security. If you're looking at the substation security, frequently discussed into this world after certain attacks at the grid, and I believe they are pretty much daily, even if you don't hear officially and publicly about it. There are NORC and FERC organizations talking about this substation security. What could help in that regard is blending your substation into the environment. And if you look at the right picture, a typical conventional substation shown with approximately 100, not approximately with 100% size. The gas insulated substation on the lowest part shows with 10% of its space requirement. So we reduce the space requirement of a substation drastically. And with its reduced space requirement, we are capable of installing the substation inside the building. We can install the substation in places where we would actually typically not be able to install substations. We can create in downtown areas, in urban areas, load centers, which operate safely and undetectable from the outside. Pretty much a nice, also ethical way to hide substation. The big advantage is also to reduce the cost for security measures compared to air-insulated substations. With a smaller substation footprint, you run less fence, you run less grounding grid, you have to install less cameras, you have to install less protective measures around the substation, which reduces the cost of the overall substation project. And last but not least, to talk a little bit about the reliability. I mentioned reliability is a big aspect in today's operation of the grid, and outages are not welcome. And we saw that a couple of weeks ago happening in the area of Texas, where a cold snap created issues on substations, tripping breakers or creating with icing of disconnect switches, situations where substations had to be interrupted. Installing a GIS, which is much smaller than a conventional substation with 10% of a footprint inside of a building, creates an environment where you actually can install that equipment safely, environmentally protected, and create a higher reliability on your overall substation. With the weather-independent O&M, you automatically also create reduced project risk. That substation can be installed, I don't know, in 6 weeks, whether it is snowing outside or if the sun is shining, the time will be the same. So the overall project costs are reduced. The installation costs for an O&M are also very easy to calculate. You know when you can go into the substation, you can do maintenance. Even in winter time, you can do maintenance any time of the year on that substation. You are independent from the environment around. What technology we have today available on the market? From the left to the right, it's pretty much, let's start with the left side, from the 69 to 138 kV equipment. We have our ELK04 and the ELK04 170, two products which are used to the 138 and 161 kV market, with the possibility of normal current ratings 3000 and 4000 amps to match requirements which you have on the typical conventional substation markets. The rated short circuit current on that technology is 40 to 50 or 50 to 63 kA, which can be used similar to conventional technology. If you go to higher voltage levels, we have a ELK14 for 245 kV, where we can go actually to 4000 amp and 60 or 80, 63 or 80 kA short circuit rating. Or we can go to the ELK3, a product used for 345 kV over 500 kV with current ratings up to 5000 or 6300 amps and the same high short circuit ratings. We have a hybrid GIS, and hybrid means in this case we are using GIS components which we are interconnecting with air insulated substation. That technology usually used in the 345 and 500 kV range and also available in the same ratings, the 5000, 6300 and 63 and 80 kA short circuit rating. And then we have our green technology with the eco or hybrid eco technology, which is available in three-phase and single-phase, and we'll come to that issue a little bit later. The technology is available up to 138 kV, 440 kA, and 2,500 amps. Hybrid Eco GIS is actually available up to 345 kV, 3,000 amps, and in the ratings 50, 63, and 80 kA. And last but not least, that nice red part, we have a digital solutions that are technologies in today's world. There are NCITs, and that stands for non-conventional instrument transformers are used. Monitoring systems are used, that meaning gas monitoring, circuit breaker monitoring, parcel discharge monitoring systems, which can be used within the GIS. You are capable of interconnecting that equipment with 61850 to the overall SCADA system and create with that a digital system utilizing the GIS technology, similarly you would do to conventional substations. With all that technology, how do you make your decision what is the right product and how to move forward? If you are seeing on the right side, that is not the worst, but also not the best what we received on a request, and showing a number of breakers and requirements. It is of course good to know the ratings of the equipment. That means it's good to know the voltage level to start with, and it's also good to know the current and the short circuit current of the equipment, as that will, for example, define certain changes in the technology used for your application. If there are specific requirements on the BIL, and here that means the lightning impulse voltage, that would be also something it would be good to know. If there are, for example, specific requirements, if you have a 500 kV with 1800 kV BIL rating instead of a typical 1550 or 1675 kV BIL rating, or if you have, for example, a 138 kV where you ask for a higher BIL rating of 750 kV, it would be good to know that such applications are available, but they would of course change the technology which would be used by engineering for deciding the product. Next step, of course, it would be good to know, do you want to have a ring configuration, 1.5 single bus bar, or whatever layout you come up with, and the type of connections. Are your plans to go with underground, overhead, or transformer connections? What are your ideas to modules like surge arresters? What are the instrument transformers requested? How does your protection system looks like? Or are you planning on any future extension? And last but not least, if it is possible to know the temperature. And North America is pretty large and the US itself is very big, so you can have temperature requirements in Arizona where we have already in the mid-90s up to, I believe, 55 degrees C in the specification, while you go further north and you see easily -40, -50 degrees C in the specification, which could have impact on the design of a substation. So we would, for example, do overload calculations that would be done SF6 calculations to see that the technology will fulfill the requirements of its specific requirement. And are there other specific environmental conditions, seismic, for example, wind loads, high altitude, that are items which make sense to have in the specification and to review. And as more as what such information is available, as more accurate will become the outcome of the drawing, will become the outcome of a technical specification. And just to give you an idea for the layouts, for example, Everything what you do in today's world in the conventional substation design, you can do in a GIS substation, in a gas insulated substation. We can do double bus bar, the single bus bar, and that both substations are, for example, indoor substations, or we can do the 1.5 and a ring, and they are, for example, outdoor substations. So you can have substations in different applications, indoor or outdoor, and you can have it substations with different layouts. The modular concept of its substation will actually allow you to use the same modules. So the double bus bar uses the same modules as the 1.5 breaker schematic. You will use the same modules, you just will arrange them differently to arrange them into the substation layout. Makes spare part concepts rather easy, makes for your system if you have different layouts like ring configurations and 1.5 configurations. The metering and protection scheme for a conventional substation and for a gas insulated substation are the same. It's the same protection scheme. You will have for a gas insulated substation usually a local control cabinet interconnected, which are functional as an interface between the GIS equipment and between the protection system. But from the metering and protection scheme, we are talking about the same system. And as I mentioned before, the GIS, either way, indoor or outdoor, both ways can be installed depending on the environmental conditions of a substation location. So with that knowledge, knowing the single line, knowing your general connections, single line diagram, layout and section views will be created, and as well and specification, which will technically specify what is the product, what are the product ratings, the configurations of the product, and will be supplied for your use, so you can actually with that evaluate your substation project. While it is not so easy to look through an 2D drawing and to evaluate exactly, is my bus really high enough? Do I have the necessary clearance? In today's world, it is rather easy to do the same in 3D reviews. And that is something I invite everybody to utilize the technology in today's world. It is really much easier to go with the entire team, and I mean really from engineering to operation through a substation, review access points, review filling ports, density monitors, review maintenance access, or during the review whether I actually fit my substation into the overall, or my GIS into the overall substation. How do my interconnection looks like to the transformers, to the overhead lines? These 3D layouts are available in pretty much every possible design with PVC, step files, 3D, PDF, which allow you to do that reviews, even if not you have the latest AutoCAD drawings available on your computer. Now this slide shows as well there's a three-phase GIS on the left side and a single-phase GIS on the right side. What does that actually mean, and why do we have actually that two different designs of the GIS? So the three-phase, let's start with the left side. It makes it easier with a three-phase GIS. So three-phase actually means that you have all three phases in one enclosure. And if you look at the lower left picture, you see the enclosure, you see the three conductors, and that is all in one gas compartment. So you have all the three phases within that one gas compartment. The big advantage is of this technology, you have a smaller amount of modules. You have, instead of 3 modules, you have 1 module. You cover everything within 1 module. You have less numbers of density monitors, lower number of mechanisms for disconnect switches and circuit breakers, lower amount of cabling with such technology. Lower amount of modules means automatically also lower failure rate. So automatically the mean time between failure of such technology will increase. The technology in the three-phase design is usually used up to 161, 170 kV. That is the typical rating for the technology. But what doesn't mean that there are bus bars available 230 kV, 345. I believe the largest ever installed three-phase bus bar was 800 kV. So there are no real limitations other than that the distance between the conductors is designed to the face-to-face voltage, and that means you at a certain voltage level it becomes not very handy to handle such large compartments on site and assemble them, seal them, and assure and safe operation. So that is one of the reasons that this technology is usually used for the lower voltage levels. On the right side, on the other hand, we have a single-phase GIS. Same technology, same idea of the technology, other than that you have each conductor inside of one enclosure. Now with each conductor in each enclosure, you actually have a smaller distance between the face to the outer enclosure. You have a face to ground voltage there, but on the other hand, you have now 3 density monitors. You have a grounding on each and every enclosure. You have a grounding between the enclosures for return currents. And you have as well to make sure that you have drive mechanisms for all 3 phases on the disconnect switches, grounding switches, and on the circuit breaker. So at the end, the idea is that the mean time between failure for higher voltage levels will be slightly less than compared to the 3-phase technology. If we have such GIS and both bays, for example, show a double bus on the left side and the cable connections on the right side, that would be a typical circuit breaker position installed inside of a substation. How would such an interconnection to the grid look like? And we have 3 possibilities to install or interconnect our gas insulated substation to the typical grid. One possibility is the cable connection. And the high voltage cable technology developed pretty fast over the last years. So solid dielectric cables are available in the ratings up to 500 kV. The XLPE technology is really used very frequent on the market. So all typical solid dielectric cable can be interconnected to GIS. You can also connect fluid-filled cable, whether it's a high-pressure fluid-filled cable or low-pressure fluid-filled cable, the same possibility. And we see on the right lower picture that is, for example, in high-pressure fluid-filled cable interconnection to a 138 kV GIS, or we see from time to time gas-filled cable with high-pressure gas-filled cables, which are also can also be interconnected to the GIS. So if you have such cable designed, you are not requested to have that cable removed and replaced by something different. All cable types can be interconnected. The same is true for all cable suppliers. It is not something the GIS supplier will come and tell you you have to use a specific cable supplier. All cable suppliers can be interconnected. The cable connection itself are rather flexible, and that means if you see on the lower left picture, you see the cable connection to the top. So this substation is installed in a basement, and the cables are going to the top outside of the substation. You can have them vertical, you can have them upside down on the right top picture. There are no limitations in that regard, making the substation installation and interconnection to the grid flexible. If you use plug-in cable connection, like a typical named Pfister type, even if pretty much every supplier, cable supplier in today's world has such a plug-in cable connection available, that is what we are having on the left top picture. But such type of plug-in connection reduces the gas work during the installation and testing of the cables and the GIS, and reduces the interface discussions on site, because you can finish your GIS installation before you finish your cable laying or cable installation on site which reduces the risk in project and at least improves the coordination for the project manager. One aspect of the cables and not so much mentioned is the substation security. We mentioned that before. Hiding substations is definitely easier with using high voltage cable, where you can place substations inside the building and on the outside, nobody will know what is going on inside. Another application is the SF6 to air pushing. And that SF6 to air pushing is available in the ratings from 69 to 1200 kV in today's world. That is a typical interconnection to overhead lines, other substation modules, for example, interconnecting GIS with existing air insulated parts or transformers. The bushings in today's world at least are available in silicone or porcelain, even if the trend is going more and more to the silicone insulator, just because of the safety of this silicone insulators and the higher availability. The bushing itself supports the interconnection, as I mentioned already, to existing AIS substations, which plays a big role if you, for example, try to refurbish an air insulated substation and want to place a GIS on the site, so you don't have to change your interconnection to the existing conventional bus system. And last but not least, the transformer direct connection. This connection is something, let's say, special and not so frequently used in the utility world, but rather frequently in the world of the industry. For one reason, there are no air insulated parts between the GIS and the transformers. That means there's no way for an external arc outside of between the transformer and between the gas insulated substation. If you have an installation close to a refinery, close to an LNG plant, that are definitely items which have to be considered as an advantage. It also plays a role if you install a substation close to public places. Let's say you build it right beside the stadium, you build it beside the school, or inside a building. Such interconnection definitely can be of advantage in such applications. It requires a closer coordination between the transformer and GIS supplier, but I would say that is in today's world a standard and can be easily accomplished between the GIS suppliers and transformer suppliers on the market. What are our considerations for designing in GIS? The building around the GIS is pretty much, it's very flexible. It can be anything from, I would say, a wooden shed up to a high-rise architectural building, whatever it is needed and whatever, how much money is available and how much the budget allows for. There are no requirements from the GIS, what is the enclosure around it. As I mentioned, GIS can be installed outdoor. The big advantage of the equipment still is for indoor installations, just to protect it from the environmental around. And that is also the point I show this specific design here. For example, this is an elevated substation, which is elevated above flood level, and which allows you to take the substation above the flood level in the region. That would be also installations in wetlands. If you have specific places where you want to get the substation above ground, close to the shore, that would be a typical installations where you would use such building. And such building actually eliminates the need for high voltage cable trenches, for high voltage cable trays underneath the substation, where you can actually connect directly to a duct which is underneath below the substation design. Inside of such building, you're really avoiding any kind of pollution. You avoid lightning strikes. So the building itself is might have a lightning strike. The equipment inside is protected. You avoid animals, you avoid birds, squirrels, whatever is running around in typical substations, and you also are independent from the environment inside around with the temperature range. You can either air conditioning such building or heat such building depending on the area it is installed. How would you install the equipment inside of the building? And that is something to be considered during the project design stage. Typically, the equipment would come in crates to the site, and it can be surprising how many crates are coming. In this case, for example, I believe we talk about 30 breakers. It's a rather large amount on crates which you have to store around your building or somewhere in the surrounding. So nothing to forget that you need actually to handle that crates. If you look at the equipment, in this case, it's the three-phase design, 69 to 161 kV equipment. The equipment is typically installed in larger shipping units, which are actually can be the entire bay. So, for example, on the right side, you have a complete tiebreaker floating into the substation, which is completely pre-assembled and just will be interconnected to the his counterparts on the left and the right side. While the three-phase technology is to a high content pre-assembled, the single-phase design, depending on layout, comes in smaller shipping units. And we see, for example, on the left side, the picture with a larger number of breakers that are 345 kV breakers, which are assembled here. And to make sure that you get through such a puzzle and then can have it assembled the right way and get your finished product. Yeah, your finished product is the gas insulated substation. A typical project or typical GIS comes together with a technical advisor who will provide and the oversight during the INC, and did not the oversee. He will provide the oversight. Will make sure that he will mark the position of a GIS on site. He will make sure that it's aligned, and that is something they are doing here currently. They are in the aligning process. He will make sure the right wire runs between the GIS and between the control cabinets, that the right interconnections are done between the modules, and he will also ensure that the gas filling process is done correctly. When all the steps are done, we are moving forward to the commissioning of the equipment, and also here the technical advisor will functioning to guide through that commissioning process. That means all the breakers are functionally tested, all the modules are tested, disconnect switches are tested, gas leakage testing is done, interlocking testing is done, high voltage testing of a GIS is done. And with a finished product, it can be handed over. Now, with a reduced time, more and more projects are fast track. How can that risk be taken out that you realize in the last minute, okay, something is missing, something is broken, something is wrong? An approach here is the IMP, and that is actually stands for that wonderful word, integrated multifunctional products, which nothing else means e-house or container in a GIS in a box. As the slide on the left side shows, the idea is actually to reduce the risk and move it forward in the project. That means if you can realize any flaws in the design, in the assembly, in the testing, and move it forward inside the project, the cost and the impact, the risk for the project is reduced. There are different ways for building such IMPs. That could be just a typical skit, which we show on the IMP light. We have an IMP standard, which means that we have a skid with a housing around, which can be in the range from 69 to 345 kV, or we have a possibility of an IMP with multifunctional houses, that is multi-housing units, MHU, and we can get a step forward in having everything included, including the battery system, protection system, auxiliary systems, which goes a step forward. Below that graph, you see the move forward from an air-insulated switchgear to a standard gas-insulated substation to a multifunctional product housing. As you can see, you're still getting the same outcome on the substation, but you reduce the footprint of a GIS. You're having ultra-compact design. And that is pretty much the idea of such housing. Further reducing the footprint of a substation, further removing the risk out of a project. So the installation of a GIS inside housing will happen within the factory, within pre-designated factory units, and the complete wiring testing will be done, or at least to a large content, wiring and pre-assembling will be done. The equipment will be high voltage tested, and that housings are protected against pollution, corrosion, seismic, high altitude, the same as a typical building is. How does it look on a real project, for example? If you look at such a technology, on the left side we see that skid standing in the manufacturing unit during the high voltage testing. The complete wiring between LTC and GIS is done. The gas is filled at the transport pressure. As I said, the testing is done. Then you do the logistics, and the e-houses are sized for the final location. That means the location is clear, the road is clear, it is clear there is no bridge in between, which could avoid any logistic or could create a logistic issue. And an important aspect, the e-houses are usually manufactured to the US specification within the US. So that is a very helpful aspect, going through building codes, going through different codes on such housings. The installation at site of such units is nearly weather independent, and I saw houses installed during snowstorms. You would, I say, nearly weather independent. You don't want to go too drastically on it, but it is with a nice coordination. This can be done nearly at every level with limited civil requirements. Where you typically have a lot of civil requirements in a conventional substation with installing foundations for each breaker, each disconnect switch, for each instrument transformer, or where you build a housing for the GIS. In this case, the housing is actually your transport cover, or your transport cover is the housing. On the right side, we see a finished product, which could be as a fast-track product for a new substation, or if you do a refurbishment of a conventional substation, interconnecting additional breakers to a conventional substation, that are fast and easy applications to be utilized. One interesting aspect, as easy as it comes in, it can also go out or can be relocated. That means you can relocate your substation by need. Some possible variations on the left side, for example, for a data center directly under the right of way for the data center, interconnecting that substation. We see a mobile substation where a truck is moving the substation from breaker position to breaker position during a refurbishment process. We see an industrial application interconnecting by cable, which was needed for an extremely fast interconnection of a grid. And here you, for example, can see the horizontal high voltage cable connections, which made the installation super easy. Or you see on the right side a typical utility for breaker ring interconnected to the transformer and to the medium voltage equipment. I mentioned it before, but we have a global aspects of the technology, with SF6 gas having a global warming potential of 23,000, or in this case, it's 23,500. That factor comes with a lifetime of the molecules in the atmosphere. And as we can see, SF6 really lives very long. It lives 3,200 years. So whatever we are bringing into the atmosphere today, a couple of generations later, it will be still there. And that is, of course, an aspect which we should not forget and should be very, very careful with handling this gas. To reduce the amount of SF6 which is stored within the technology, within the GIS equipment, there are ways to reduce that number of that gas and using different gas mixtures. And one of the gas mixtures used is, for example, AirPlus, which is a gas mixture which is typically using components like N2, O2, CO2, and fluor nitriles, fluor ketones as additives in that mixture. The gas, actually, the outcome is a highly reduced global warming potential for that gas, which means not that we should not handle it the same way of carefulness, but we might feel less guilty to our next generations with having the SF6 inside of the compartments. There are technologies already on the market and already available, like, for example, this technology, the ELK04 AirPlus, which is a technology up to 3000 amp and then 138 kV, 40 kiloamps, which is utilizing, for example, background gas with CO2 and O2. So that technology, it looks like a typical GIS. It handles like a typical GIS. It is pretty much the same, but with a different gas filling inside of the compartments. And while this one is in 138 kV, and now question could be what is happening to the higher voltage levels. There are also developments in the higher voltage levels, like this, for example, an application in Germany, and there are other applications in other parts of the world. Where, for example, AirPlus is utilized for the passive components in temperature range up to -30 degrees C. That passive components making a huge part of a GIS equipment. That means up to 40–50% of the GIS is actually passive components, which will be filled with the AirPlus technology, and with that reducing the SF6 in the GIS. The future idea is actually to reduce the SF6 in the entire GIS. The future idea is actually to reduce it as well in the circuit breakers and all active switching components within the equipment. That are development steps which are ongoing, and there we see future developments ongoing. One of the ideas actually, and that is actually for the 420 kV the case, is the hybrid eco. That is actually the idea, having the circuit breaker still operating on the SF6 while utilizing the AirPlus gas, the non-SF6 gas, in the components around the circuit breaker. Big advantages, the limitations to the ratings in the grid are reduced. Typical with the AirPlus technology in today's world, usually the limitation is 40 kA for the circuit breakers which are on the market. With the hybrid solution, ratings 50, 63 kA or even higher can be reached, and would allow for reducing the SF6 content within the substations drastically. Another aspect during the development of the technology as well, the sealing design is changed from the GIS itself, and it's here under the name Super Seal. It's actually an idea to reduce the seal, the leak rate of a technology. And that's not just for the EcoGas, but same is of course true for the SF6 as well. So there's an aspect, so you reduce the amount of SF6 in the GIS technology while also reducing the leakage rate of the equipment itself. And with its reduced leakage rate, you also have a much lower environmental impact with that technology. Of course, we don't want to leave customers or alone with such technologies, and there's an entire circle around that technology to ensure safe operation and safe handling. That starts with the design of the technology, like monitoring for the gas, like filling of the gas inside of the technology, which is usually done by the manufacturer. The service units are available already by Dilo, for example. Their service units are available, mixing units are available. You have leak detector for that eco-gas technology, and you have tracers for any and analyzers for the technology as well. So we've had an entire circle from the safe installation, safe operation, and maintenance to the final dispose of the gas handling is already in place for that new technology, and it allows us to look into an more environmental friendly future for this GIS technology. So that's it from my side, and let's see whether we got any questions, and I will hand them over to Viper. Thank you.
Thanks, Thomas. I'll take over for the Q&A. We still have some time for a few more questions if you want to enter them into the Q&A widget, but we do have several here that we'll just start taking one by one. So first, does your GIS allow extension of future bays without taking a shutdown of the current bays in operation?
I assume if Viper doesn't answer, I will do it. Yeah, yes, it is actually from the technology. It is the same as in conventional substation. If it's in part energized, of course you cannot touch it. So if there's a future extension, the extension has to be planned in a way that you can avoid any shutdown, either of a feeder or of a main bus, and that can be done. So we would recommend to, and that was also part of the requirement, if your future extensions planned, automatically bring that into the design stage, and we can integrate such ideas into the overall layout of a substation to avoid shutdown of feeders or main bus bars during extensions. Yes.
Okay, Thomas. Our next question is, what is your recommendation for deciding between an indoor versus outdoor GIS?
Yeah, I would usually all the time say go indoor, because you would not repair your car on the street, but usually deciding factors are temperatures. If the temperature goes below -30°C, typical breakers, and that is also true for conventional breakers, would need additional support, like heating blankets or heaters for the circuit breakers. With the GIS having more modules, that is something you try to avoid, and you would go usually indoor at such temperatures. And another aspect is being close to a very corrosive environment. That could be extremely close to the shoreline. It could be close to any kinds of an industrial application. If you're close to, even if it's coal mine, ash ponds, everything what creates an hot ash mining, everything what creates an environmental challenging and corrosive environment, I would definitely go for indoor applications. Well, all others are up to the customer, but my recommendation, that equipment is so small and does not require any architectural buildings. That building layout really does not add too much to the substation, but adds a lot to the reliability, accessibility during bad weather conditions, allowing maintenance during such inclined weather conditions. I would recommend indoor every day. Anderson?
Sorry, Thomas, lost me for a second. Yes. Can you please advise whether the IGA option leads to minimum site installation time as they come pre-assembled with GIS and the local control cabinet within a housing?
As the IGA installation, the idea is very much to reduce on-site installation time, and depending on the layout and design, we can easily talk about 50, maybe even 80% reduced installation time on site. The idea is really to remove the on-site labor, assure that there is no labor working on site, reduce any kind of an work on site with a technology, bringing it inside of a factory or location, making sure everything can be tested before it arrives on site, and with that actually reducing the project risk. That is the idea behind the technology.
Great. Can you confirm whether you need ventilation inside of a GIS hall?
Yes, it is highly recommended to have ventilation to assure that building can be ventilated in case of an gas leakage or in case of a failure of an equipment. For the IGA, we would actually install that ventilation from our side. For the building, it would be a recommendation from our side.
Okay. Any code requirements in the U.S. in regards to monitoring?
I would not know what in regards to which codes could be required. Either the monitoring systems can be interconnected based on the protocol, the 61850 IC 61850 protocol or the DNP3 protocol, but that is not really a code. That is the protocol for the interconnection to the SCADA system. Other than that, I would not know any requirement which requires a monitoring system. The monitoring systems are a nice add-on. You have a lot of SF6 compartments, and it is of advantage to see any trending on the SF6 values. If you see any trending on a possible gas leak, so you can early react, avoid the losses, and also can do a better planning on your maintenance. But there is no standard which requires a monitoring system.
Okay, and I think we probably have time for one last question. So what is a good rule of thumb of when to use UG power versus GIB? Is there a certain length that one is a cost benefit or to the other?
Can you repeat the question?
Sure. What is a good rule of thumb when to use UG power cables versus GIB? Is there a certain length, or is one a cost benefit to the other?
It's actually a question I cannot answer, and I would recommend maybe to reach out to us with an email so that you can actually forward dig into that question. I would not know an answer to this question right now.
Okay, great. Yes, we do have a whole lot of questions that came in pretty rapidly that it looks like we're out of time to get to, but just know that we will answer you directly via email after the event. So in wrapping up, I appreciate your attendance today and hope you learned something new. Please remember to take the survey before leaving and downloading your certificate by clicking on the icon in the certificate widget. So thank you all for attending and have a wonderful rest of your day.